Hi, ladies and gents. Today we're going to take a look at how to do hypothesis test problems for the population mean and the population proportion using Excel. Now, I introduced you to a couple of problems in Unit H. Actually, there's about 4 problems here. I'm going to walk you through 3 of them and just briefly mention the other one. But the first one was the nicotine example. This is on page H2. And I thought what I'd do here is just go back to our note manual. And this is where we did this by hand. So let's walk through this really quickly here. So the problem is that the manufacturer of a certain brand of cigarettes claims that each cigarette contains on average no more than 1.6 milligrams of nicotine. That's actually the standard that is being tested against. And if the manufacturer is significantly higher than that, then there's a problem. So an independent testing agency comes in. They take a sample of 144. We get a sample mean of 1.7, a sample standard deviation of 0.5. And the question is, does the sample support the claim? So there's our hypotheses that mu is less than or equal to 1.6 against the alternative that mu is greater than 1.6. We'll assume an alpha of 5%. The formula that we use is a T formula because our population sigma is not known. And so then we went through and we worked out the computed T value. It turned out to be 2.4. And that gave us a P value, when we looked it up on a table, somewhere between 0.5% and 1%. Now that is the P value approach. We did this originally using a classical approach up here. And in the classical approach, it differs only in that we have a critical region here determined by a critical value associated with the alpha. So the 1.645 is the critical value, and anything above 1.645 when you convert it into a T would end up being in the critical region, the rejection zone. So that's how we did that. So how do you do that in Excel? Let's take a look at how that's done here. So again, we're going to take a look at that first problem, H2 on your manual. And let's go back here. And I want to take a look at this page right here. So what I've done here is I've actually reproduced the sample here. Had to do a little bit of calculating here so that the mean turned out to be exactly 1.7 and the standard deviation was 0.5. But I've got a bunch of values, 144 of them, and let's take a look at how we would do this in Excel. Now, one thing we could do, of course, is to get out our calculator, and we could figure out a mean. We would use an average function to get that, and then we'd figure out the standard deviation, and then we could stick all that into a formula, pull out the calculator, and get a T star value, and then we could use a T dist function. But there's got to be an easier way to do that, isn't there? Let's take a look actually under the data menu. And under the data menu, you've got the data analysis tab. Now, this is going to be useful, of course, for giving you the essential descriptive statistics. So the descriptive stats will give you your X bar, will give you your S, and will give you your N, and then you could calculate by hand. But is there something better? If we go down to the bottom, we'll see that there are T tests and Z tests. That looks like we're in the right area. The problem is that they're for 2 sample tests. And we're only dealing with 1 sample. But is there a way actually that we can use that? And the answer is yes. We're actually going to use something here called the t-test 2 sample assuming unequal variances. Let me take you really quickly here over to Business 307, which is the next stats course. And you don't have to know this, but I want to show you where we're going and why this works here. When we get into Business 307, we'll be taking a look at 2 sample tests. And so in this particular case then, the generic case, is that the 2 means from 2 different populations are equal. So the mean from population 1 is equal to the mean from population 2. And then we'll go and we'll take a sample from each one. This can actually be rewritten this way, that the difference between the two means is equal to 0. That's going to be important. The formula that we use here is a Z statistic, or we could use a T. So if we have a T star because sigma is not known, then these would be S's. But it's the same formula here that we have here, okay? Now, here's the thing. When we hypothesize that the two population means are the same, then that means the difference is equal to 0. That effectively means that this crosses out. What we're going to do is we're going to set up a second sample. We're going to fool the computer into thinking that we have a second sample, and it'll actually be this guy right here. Let me show you how you do that. And we'll come back to this particular page in a bit here. So I'm going to go back to Excel here. And before I go into using this t-test, assuming unequal variances, I have to cancel that. What I'm going to do here is, this is my first sample. So let's call that sample number 1. Of course, you don't have to type this out here, but I want to show you where we're going here. This is going to be sample number 2. And what it is it's the hypothesized mean twice. You need two values in order for it to be able to calculate a standard deviation of those two. So that 1.6 is the value which is in HO. And so you put that down twice. Now we're going to fool the computer into thinking that we have two samples, one from one population, which is really the only sample we have, but we're going to fool the computer into thinking that this is a second sample. But all it is it's the hypothesized mu. So let's go back over here and say the mean, of course, of two 1.6s will be 1.6. And so this mu, if we were using our example from the nicotine example, that would be the mu naught is equal to 1.6. So when you put down 1.6 and 1.6 in a separate column, then the sample mean, of course, would be 1.6, which is the population mean. Down here, what's the variance of two numbers which are the same? Well, the variance is equal to 0. And so what happens is that this term completely crosses out. And what you're left with is x bar minus now mu over the square root of S1 squared over N1 squared N1, which is exactly our formula that we use for standardizing, right? If you took the S1 squared out of the square root, you just have S, and then you've got over the square root of N, right? So that's how we fool the computer into thinking that we have two samples, when in fact we only have one. So let's go back and do this in Excel. So once again, I need to set up these three guys here, give it a title, and that's because I've got a title over here. So I've got a title for our sample, and then I've got a fake sample over here. So it's 3 cells. It's a title, hypothesized mu, and then the value which is in the null hypothesis twice. And you need it twice in order for it to be able to calculate a variance. And the variance of those two will be 0. All right, now let's go and do this thing. So we're going to go to Data, Data Analysis, and we're going to be using a t-test for a 2-sample assuming unequal variances. When we get at 307, we'll talk about the other types of tests here, but we're just going to focus on this one here. So press OK. And this is what it gives you, a little dialog box that looks like this. Now, the variable 1 range is just this original sample. Notice that I'm including the title at the top there. the nicotine sample. And I go all the way down, 144 observations. The variable 2 range is, let me scroll back up here, are these 3 guys right here. The title and then the 2 1.6s. The difference between these two is hypothesized to be 0. Remember I said that that was important? So that's going back over here where we're saying this part up here in red, that mu1 minus mu2 is equal to 0. So we're hypothesizing that the difference is 0. So you put in 0, tell it you got labels, because we included those. You can choose a level of alpha, but it defaults to 5%. And then the only other thing you do is you put down your output range. So I'm just going to choose a cell here. Yeah, let's do it maybe over here. And press OK. And let's see what we get. Okay. What I would probably do is just clean these up a little bit here. So I'm going to take these down to about 3 decimal places. There we go. And then that's pretty much what we've got. Now, this column over here that says hypothesized, this column over here which says hypothesized mu is, we can just really ignore that. It's our 1.6, and then the variance of 2 numbers the same. The 2 1.6s is 0, and there was 2 observations. But here's the important part. This guy here is x bar. So in the mean column here, you've got your x bar value. And then, of course, this guy right here is your mu naught. This is your variance. That's actually s squared. Okay, so 0.5 squared gives you 0.25. And then here's our n, 144. And if you put all of those into the t star formula, x bar minus mu over s divided by the square root of n, you would get this guy right here. So the t stat value is your t star value. Degrees of freedom, of course, is n minus 1. And then this was a one-tailed test. So here's the important statistics that we need right here. The p-value, remember when we looked this up in the table, we figured that it was somewhere between 0.5% and 1%. So this shows that it's 0.009. The critical t-value, well, we said it was 1.645, but that's because the t-table only goes up to 120 degrees of freedom, and then it jumps to a z row. And so the actual t-value would be 1.656. Now, one thing to note about this is that it doesn't specify whether it's positive or negative. It'll always show up as positive. In our particular case, though, the alternative hypothesis was that mu was greater than 1.6, so the critical value was positive 1.656. So what we would do then is we could either say the p-value, I'm going to put that in a different color here, of 0.009 is less than your alpha of 5%, so you would reject HO. Alternatively, you could say the 2.4 t-star value is greater than the critical value of 1.656, and therefore reject HO. And that's how you do it. Let's take a look at a couple more problems. So we had another problem here, the breaking strength example. This was on page H11. So I'm going to take you back here. We have to go back to our original set of notes here. And we've got the breaking strength problem back here. The mean breaking strength of a type of steel is being determined from long use to be 20 kilograms with a standard deviation of 2.8. Now that's important to note that that's a sigma, a population sigma given. So then we take a sample because a research engineer claims to have developed a superior wire. And so we take a sample of 100, we get a mean of 21. And the question is, what do you think of the researcher's claim? Do we have a superior wire? So if you look at the HO and the HA down there under the classical approach, you'll see that mu is less than or equal to 20 is the null hypothesis. The wire will be considered to be superior if the breaking strength is significantly higher than 20. So the alternative is that mu is greater than 20. Now, the important thing to note is that when you go through the flow chart, you find that you use a Z formula, not a T formula, because sigma is given. It's 2.8. So let's go over and see how that's done then in Excel. In Excel, what we do is we go over here and we've got our steel example. I've got numbers here that actually average out to the sample mean that's given here. And the hypothesized mu, again, we're going to set up a dummy second sample. And what you're going to do is you're going to put in the hypothesized value. Now, you only have to put it in once. It only needs one number because it's actually not going to calculate a variance of the sample there, of the second sample, because the variance is given to us. However, I'm going to put it in twice just so that you're always using the same procedure every time you go through this. So again, you only have to do it once if you know what the sigma is. You only have to put in 120, but let's just be consistent and put in 2. So now what we do is we go to data analysis, and then instead of using the t distribution, the t-test, we're going to be using the z. So the z-test 2 sample for means. Okay, it's got a little bit more here, but most of it is the same. So the variable 1 range would just be these guys here. So that's your original sample. I'm including the title at the top that says steel sample. Might be your question number. The variable 2 range are these 3 cells here. Remember that we include the title at the top and then at least 120. You can have 220 though. The hypothesized mean difference, just as before, is going to be 0. And then we've got 2 new fields here. So it says here, well, what's the variance here then? The variable 1 variance. And if we go back to our problem here, we're going to see that our variable 1 variance, let's go back here, was 2.8. So what we do then is you get out your calculator and you just figure out what is 2.8 squared. And so let's do that. And you know what? I should have written that down. I didn't do that. So I'm just going to cancel that. And I'm going to put down 2.8. And then let's just square that. So equals that. Squared. 7.84. So that's what we want. So let's go back and do it again. All right, so z-test, 2 sample for means. Variable 1 range, these guys here. Variable 2 range, these guys here. Hypothesized mean difference is 0. And then the variance, the known variance, is 7.84. And that was that 2.8 squared. Now, the variable 2 variance is, well, what's the variance of those yellow values there? And what you want to do is to put in 0. Unfortunately, it doesn't like that. It won't take it. And so what I do is I just put in point 0.00000000001, Doesn't matter how many you get, just make it really, 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 really small. And so it basically blanks out there. All right, tell it you got labels. Your alpha is defaults at 5% here. Your output range, and we'll just go find a spot here. Let's do it down here maybe, and press OK. And let's see what we get. Okay. I'm going to take these down. All right, so here is your X bar value. This is your sigma squared value, 2.8 squared, right? That's the known variance. Here's your hypothesized mean. Don't worry about the variance. That's just scientific notation. That's 1 times 10 to the minus 12th. So that's basically 0, right? Here's your Z star value, 3.57. That's way out in the tail. So it turns out to be basically, 0, close to 0. Your critical value is 1.645. And so these are the guys that are important to look at here. Again, what we would do is we would compare your Z star value, computed Z value, to the critical value. This is a one-tailed test, upper-tailed. And so that's 1.645. And so you would reject HO. Alternatively, the p-value is close to 0, which is less than 0.05, so we would reject HO. Let's just take a look at when we did this by hand. And so by hand, we got 3.57. You can see that guy here, right there, 3.57. And that is greater than the 1.645. And then when we do it the p-value approach, what we did was we looked it up on a table, and the last number in the table was for 3.49, and so it was 0.0002, and it's actually smaller than that. So that's, we said 0.002 is less than 0.05, and so we reject HO. Again, this is a one-sided test, an upper tail test up here. And so that's how we do that here. All right, so we know how to do a test for a mean using both a t-distribution and a z-distribution when sigma is known. I'm not going to work through the next problem, but here's the psychologist problem. And this psychologist problem, I've actually got the answers here. And so in this particular case, then, it was a two-sided test that mu is equal to 120 versus the alternative that mu is not equal to 120. You do it exactly the same way, a t-test assuming unequal variances. The only thing to note here then is that we're using the t star, but then these guys at the bottom. So here's your critical value of 1.998 for a two-sided t-test. And here's your p-value. Now, when we do this in class, what we'll find is that it's greater than 2 times 10%. You'll see that later because this is a two-sided test. And then the nearest critical value is 1.96, I think. And 100 pieces, so it'd actually be closer to about 2. But this is the closer critical t value. So again, the t star is minus 1.2. You'd be comparing that to a negative 1.998. Remember, it doesn't show whether these are positive or negative, so you just have to know that this is a negative 1.998 by taking a look at how you set up your problem. Or alternatively, your p-value of 23.5% is greater than your alpha of 5%, so do not reject HO. In either case, you do not reject HO. All right, last problem I want to show you here is the advertising problem. And so this is dealing with proportions. And so in this particular case, let's take a look at the problem. The advertising example. Manufacturer contemplating a bulk advertising campaign is determined that in order for the campaign to be successful, a response rate of at least 20% is needed. Let's say that's the standard that they have to meet. So that's going to be your null hypothesis. A pilot study is taken and we get 102 out of 600 and test the null hypothesis. So we did that by hand over here. By the way, here's the psychologist claim. I'm going to go through that with you in class. Here's the test for the proportion. This was a one-sided test, lower tail. Take a look at the sign of the alternative hypothesis. And then we walk through this, and we ended up with a critical value of minus 1.645, a computed value of minus 1.84, and so we reject HO. And then you can do this as a p-value approach. And it's, the p-value approach, is minus 1.84. Yeah, we're dealing with a Z distribution. So if you look up 1.84 in the table, you find that it comes to about 3%. That's down here at the bottom in green. And so that's what we've got there. Yeah. I was thinking a t-distribution there for a minute, but whenever you're testing proportions, it's always a Z because you're using a normal approximation to the binomial. So it's always a Z table that you're looking at. Let's go back here and see how we do that. Now, when you take a look at a data set, what you'll end up with is a bunch of yeses and nos. And so do they support the campaign? Yes or no? And what we need to do first is we need to convert these all into ones and zeros. So what I usually do, I've already done this, but if this is the original sample, let me just call this the sample here. What statisticians usually do is they name this after one of the values. So call it either yes or no. Now what we're measuring here, a success, is a yes. So we should number the successes as ones and the failures as zeros. And all I do is I just simply do a sort here, like this. And then we've got all the no's and we've got all the yeses, so you can just simply type a 0 for this first no and then just copy it all the way down. Like this. Now, of course, I've already done this, but just showing you the procedure. Oh, there were 600 of these things, wasn't there? It's a long ways down. There we go. Okay. There. And then you would type a 1 for the yeses, and then you would copy that all the way down. So there we go. All right. So that's really important that you change them into zeros and ones. Now what we do is we come over here, and we're going to set up our dummy second sample. So this is our new sample. We'll call that sample 1, I guess, right? Thinking back to our original formula for a two-sided test, or a two-sample test. And then what we do is we put in here the hypothesized proportion. Because this is a Z test, you only have to put it in once, but I'm going to put it in twice just so that we're using the same standard every time. Okay, now we're going to have to put in a variance, and the variance that we're going to use here is, well, let's go back here to here. And the variance that we put in is, I'm going to put this in red, or let's say orange. It's right in here. So the variance is going to be P0 times 1 minus p naught. Now, where that comes from is, remember this guy right here? Sigma is equal to the square root of n times p times 1 minus p. It's the same thing. The variance, of course, is the square of that. The ends, they end up canceling out because of the fact that we end up dividing the, originally we divided this formula here square root of n times p times 1 minus p. We divided both sides by n, top and the bottom here, by n. And so these cancel out and you're left with this. So this is the variance. All right, that's kind of messy. You don't have to remember all that. But the important thing to remember here then is when you are asked for the variance, you put in p naught times 1 minus p naught. So in our particular case then, it's going to be 0.2. So 0.2 times 1 minus 0.2. And that'll be 0.16, right? 0.2 times 0.8. So let's go now and do this. By the way, of course, you should always show your check. Does n times p naught equal at least 5, and n times 1 minus p naught equal at least 5? And you'll find that it does in this case, so we can use a normal approximation of the binomial. Okay, data analysis. Z, right? It's always a Z test when you're testing proportions. Now, this is just here from the last problem, so let's just clean that up a little bit here. Like that. So, all right. So the variable 1 range is now the columns of zeros and ones. Right? 1 means yes, and 0 means no. I'm going to go all the way down. I'm just going to use a shortcut here. The variable 2 range, of course, as usual. Let's go up here. The variable 2 range are those 3 guys, those 3 cells right here, as before. The hypothesized p, and then 0.2 is the hypothesized p naught. And I put them in twice. You only have to actually put them in once. We're hypothesizing that the difference is 0. It's always 0 in the problems that we're going to be dealing with. And then this is where you put in p naught times 1 minus p naught. So that's really important that you remember that. So 0.2 times 0.8 is 0.16. Here you put in something really small, 0.00000001. Choose your level of alpha. Choose your output range. I might have to go and change that. Let's go and find a spot. How about down here? And then press OK. And this is what we end up with. And I'm just going to clean this up a little bit. Okay. So when we did this by hand, we ended up with a Z star here of minus 1.837. This mean, now it's important here to note that the mean of a bunch of ones and zeros is just a proportion, right? If you just sum up this column of zeros and ones and divide by n, you'll get the proportion. And so this is the p bar right here, this guy. So it says the mean, but it's the mean of ones and zeros, so it's a p bar. And then this, of course, is the p naught of 0.2. So here's your Z star of minus 1.84. Here's your p value of 0.0329. And here is your critical value of 1.645. Remember, that's actually minus 1.645 because the original problem was a lower tail test. So again, back here, you can see all of those values, right? Minus 1.84 right here. And then here's your p-value. And here's your critical value. Your critical value, we did that back here when we did the classical approach. So there's the classical approach and then the p-value approach down here. So that's how you do that using Excel. You don't have to get out your calculator and do a bunch of calculations and so on. The only calculation we did ever was 0.2 times 0.8, or squaring the variance in the case of the breaking strength problem, but everything else is done. Remember that before you go in to your data analysis Toolpak and choose your Z or your T, you have to set up these 3 cells here first. All right, and I think that's all we need. So that's going to end the lesson here.